We're going to see Stokes' theorem here, but first we're going to remind ourselves of what Green's theorem says. It says that the line integral over c of p dx plus q dy is the double integral over d of the partial of q with respect to x minus the partial of p with respect to y dA, where D is a region in R2 that is bounded by the positively oriented plane curve C. This all exists in 2 dimensions. And remember that this can be expressed as the line integral over C of f dot dr for f of xy equals pi plus qj. And these are an aside parentheses, not mathematical parentheses. We'll come back to why I've introduced that in just a minute, but now we're going to see Stokes' theorem. I don't usually just read you what's in the textbook, but hey, here we are. Let S be an oriented, piecewise smooth surface, and right now I'm going to say that surface is in R3, that is bounded by a simple closed piecewise smooth boundary curve C, but that boundary curve is actually a space curve. C has a positive orientation. F is a vector field, and I'm going to say this F is f of x, y, z. I really want to advertise that this is in R3. F is a vector field whose components have continuous partial derivatives on an open region in R3 that contains S. Then, so all of those have to be satisfied, and they will in the work that we're going to do. But the conclusion is that the line integral over C of f dot dr, that looks familiar, is equal to a surface integral over the surface S of the curl of f dot ds. And as a piece of notation, this can also be expressed as the partial looking ds, so that's just another way to write the boundary curve, of f dot dr. And just to emphasize here, the partial s is a positively oriented space curve that bounds S. Now, comparing these 2 theorems here, what we see is that C is a positively oriented plane curve for Green's theorem, and C for Stokes' theorem is a positively oriented space curve. Just as for Green's theorem, C bounds a region D, for Stokes' theorem, C is the boundary for a space region S. I said space region, I really mean surface in space. Let's bring the analogy home here. For both theorems, the right-hand side contains a sort of derivative, right? With Green's theorem, we have the partial of q with respect to x minus the partial of p with respect to y. The partial derivatives are floating around. And the curl of f is actually a kind of derivative. Remember, it's the del operator cross f, and the del operator is, its components are partial derivatives. And the left-hand side contains an original function, right? I mean, for Stokes' theorem, the curl of f is related to the line integral here with f, right? And in Green's theorem, we have the partial of q and the partial of p, I mean, with respect to x and y, but on the left-hand side, we have p and q proper, right? So the left-hand side has the original function, but also values on a boundary. So in Stokes' theorem, we have the surface S in the representation where we see curl of f dot ds. And in f dot dr, we're talking about the boundary curve C, the plane curve. Same thing in Green's theorem. We have a region D, and the value of that double integral is the same as the line integral over C, the boundary curve. This is actually much like the fundamental theorem of calculus part 2. Because remember, it says that the integral from a to b of f prime of x dx is equal to f of b minus f of a. And so the fundamental theorem of calculus part 2 gives us, on the left-hand side here, a derivative, and then on the right-hand side, values only on the boundary. In this case, it's the boundary of an interval, so particular points, f of b and f of a. So this draws together the fundamental theorem of calculus, Green's theorem, and Stokes' theorem. In each case, we're just getting higher and higher dimensional. if it happens that our space surface S is flat and lies in the xy plane with upward orientation, then the unit normal vector n is equal to the unit normal vector k. And we get that the line integral over C of f dot dr, which we've just seen is equal to the surface integral over S of the curl of f dot ds. And that becomes the surface integral over S. Folks, if the unit normal vector is k, then we end up with the curl of f dotted with k dA, which is the vector form of Green's theorem that we saw in a previous section. In this way, Green's theorem becomes a special case of Stokes' theorem, where Stokes' theorem is in 3D, Green's theorem is in 2D. So to come back up here, we've already noted that Green's theorem was in 2D. Now I'm going to note that Stokes' theorem is in 3D. Put another way, Stokes' theorem is a higher dimensional version of Green's theorem. We're going to make another note here. Folks, we're saying that the surface integral of the curl of f dot ds over a surface S can be computed only by considering the boundary curve C. As a consequence of that, if two surfaces S1 and S2 have the same boundary curve C, then the surface integral over S1 of the curl of f dot ds, which is equal to the line integral over C of f dot dr, would equal the surface integral over S2 of the curl of f dot ds. So for the two surfaces, the surface integral would be the same because they both equal a line integral over the boundary curve C that they share. A third note. I would like to remind us that ds, vector s, is equal to n times ds, not vector s. We saw that when we first saw surface integrals. And both of them equal the partial of r with respect to u cross the partial of r with respect to v times dA. The difference here in what we're writing is that n is a unit normal vector, and ru cross rv is simply a normal vector. A final note. How many of these are there going to be? This is the final one, folks. You may recall that the curl of f was the tendency in a fluid of a particle to rotate at a particular point. So the surface integral over S of the curl of f dot ds is the collective tendency of a fluid to rotate over the entire surface S. The line integral over C of f dot dr is the tendency of the fluid to circulate around the boundary. An interpretation is that the larger this value is, the more likely the fluid is to circulate around rather than cross the boundary. We're not going to prove Stokes' theorem here. The point of this was to present it to you. The author presents a proof for a special case, and as he says, the proof in the general case is for a course in advanced calculus. The proof, you are welcome to look at it, involves a lot of partial derivatives and a couple of applications of the chain rule.